a few considerations when it comes to prediction. Screening is applied at the population level among asymptomatic individuals, and we should only really apply screening if we believe that there are interventions that are effective among pre-symptomatic individuals. Otherwise, it might be worth waiting for symptoms. An individual who does not actually have the disease but is predicted to have it will be enrolled in the healthcare system unnecessarily. And disease prevalence should be expected to be much lower in a screening setting than in a diagnostic setting, and therefore we should remember the issues with PPV from demonstration 1. If screening has any side effects, then many individuals may also be exposed to them. Another concern with screening is lead time bias. Lead time bias happens when screening leads to early detection, but early detection doesn't actually have any benefits. So here we see 2 individuals who had onset of cancer at the same time. As time progressed, one of them detected the cancer through screening, while the other, cancer was detected from symptoms. And so this is the lead time, the time difference between screening somebody and detecting cancer or any other disease, and detecting the disease from symptoms. They both died at the same time, but you could almost perceive that this individual benefited from screening because the amount of time you followed the individual is longer than this individual. So you have this as the perceived survival time, and this is the perceived survival time for the individual whose cancer was detected through symptoms. And then lead time bias is when you assume that because this particular individual had a longer survival time because you knew of their cancer longer, that screening had benefits. But in this case, screening actually didn't have any benefits. So lead time bias, when you attribute benefit to simply observing people. Another type of bias in screening is length time bias. So let's assume that you have the same number of fast and slow growing tumors over a period of time, let's say a year. Now, by chance, screening will find more slow growing tumors. So you see here, this individual had a fast growing tumor because they had symptoms here and then they died. While some other individuals had a slower growing tumor, and so they lived with the tumor growth for a longer time. Now, by chance, if you pick one time to screen here throughout the year, you're more likely to actually capture individuals who have a slow-growing tumor. So, people with a fast-growing tumor will be diagnosed when they get symptoms, while people with a slow-growing tumor are more likely to be diagnosed at screening. So, length time bias is concluding that screening has an effect on cancer progress and risk of death, when in fact slower growing cancers are oversampled by screening. In general, when it comes to prediction, one of the trickiest things is having a gold standard. So to assess predictive performance, you really need to know if an individual is a case or not. You need to know if an individual can be put in the Y+ or the Y- category. If you don't have that gold standard, then then your estimates of your predictive performance, whether it be calibration or specificity or positive predictive value, is going to be biased based on if you're categorizing people in Y+ or Y- differently. An old friend, missing data and selection bias, is going to be an issue. If you base your predictions, and if you use a model and you base your predictions on data for which there's systematic missingness, then findings are biased. And therefore you cannot generalize as easily because data points are not collected from a true random samples. If we continuously screen but screening oversamples people with high risk, then we create a selection bias and PPV might be inflated. Measurement bias. Even with a perfectly random sample from the correct population, you may still be measuring something incorrectly. You might have different methods for measuring Y plus and Y minus classification, biasing the estimate of prevalence. And we've discussed that before, how defining a case and a not case may be different. I should say that's not always a problem. So the link between cancer and smoking is not really dependent on if a person smokes 20 or 25 cigarettes per day. Smoking cessation interventions targeting smokers in general may be helpful regardless of the exact number of cigarettes they smoked. So I wouldn't obsess too much about measurement bias in those cases where a rough estimate is just as good as an exact estimate.